In this video, we will discuss about filters and their characteristics, and then we will follow it with some definitions in this unit like signal bandwidth, system bandwidth, and distortionless transmission. So first, let us start with ideal filter characteristics. So what is a filter? By definition, filtering is a process by which amplitudes of frequency components in a signal are modified, right? That means if there is a signal with different frequencies, let us say my signal consists of three different frequencies: omega 1, omega 2, omega 3. These are the three different frequencies. So what does a filter do? Filter, it changes the amplitude of these frequencies. It changes the amplitude of these frequencies. Suppose I have amplitude A1 for omega 1, A2 for omega 2, and A3 for omega 3. My filter changes these amplitudes to a different value. Let us say some B1, some B2, and B3. This is what a filter does. It changes, or um, it modifies the relative amplitudes of the frequency components in a signal. It modifies the amplitudes of the frequency components in a given signal. That is what a filter does. So how does this filter modify this relative amplitudes? Based on that, we will have different types of filters. So we have four different types of filters. The first one is a low pass filter, and then we have a high pass filter, and then band pass filter, and then finally band reject filter, band reject filter. On top of all these four, we have one more filter that is called all pass filter. All pass filter. So we'll look at the characteristics of each of these filters now. So this is the low pass filter. Low pass filter. So what does the low pass filter do? In the name itself, it tells us it allows, or it passes the low frequency components. My signal, let us say I have frequencies ranging from, let me say, 100 till 200. This is my frequency range, or let me say for simplicity purpose 0 to 200. These are the frequencies I have in my signal. Now if I take a low pass filter, that allows up to 100, up to frequencies of 100, then what will happen? Only from 0 to 100 my frequencies are passed through, and the frequencies above 100 are rejected. The frequencies above 100 are rejected. That is what low pass filter does, right? So if you look here at the characteristics of the low pass filter, this is h of omega. Let us look at this as h of omega, right? H of omega. It is against omega. So what is this? This is a low pass filter. So it allows frequencies from minus omega c to plus omega c. These are the low frequencies, right? From 0 to omega c and from 0 to negative omega c. These are the low frequencies. So these frequencies are passed through, and frequencies greater than omega c are rejected. These frequencies are rejected. It allows only the low frequencies to pass through, and it rejects the higher frequencies. That is the filter characteristic of low pass filter, right? So what does the low pass filter do here? The low pass filter passes all input signal components, that are all input signal components that have frequencies below omega c. If the input signal components has frequency below omega c, then all such components are passed through the filter. If all the frequencies above omega c in this region, all the frequencies above omega c are rejected. That is the function of low pass filter. So all these filters that we're going to discuss now are ideal filters. Ideal filters, right? So what is the ideal filter? What do we mean by ideal filters? Ideal filters means this is how a filter has to exist. This is the most ideal way of a existence of a filter. Exactly at omega c, the filter characteristics drop from 1 to 0. This is 1, right? The amplitude drops from 1 to 0 exactly at omega c. This is the ideal low pass filter. Now this is the low pass filter. Then we'll see the definition of we'll see the now we'll see how we can write the h of omega for low pass filter, right? H low pass filter of omega. How is it defined? How is it defined? It is defined as, if you look at the picture here, it is defined as 1 for omega less than omega c, right? 1 for mod omega less than omega c. This is omega c. Then, and for all other values it is 0. So 0 for mod omega greater than omega c. That is how we'll define the transfer characteristics of low pass filter. This is h low pass filter of omega, right? Transfer function of low pass filter. This is the magnitude characteristics. Now we should also look at the phase characteristics. Phase characteristics will look something like this. All these filters we are going to discuss now will have linear phase characteristics. They'll have linear phase characteristics. So how does the phase characteristic look like? It looks like this. Ideally it has to be linear, right? It passes through 0, right? This is how a phase characteristic must ideally look like. Now since uh, now if you write the phase characteristics, how are we going to write the phase characteristics? The phase characteristics is equal to theta of omega, right? Theta of omega, it is equal to this is nothing but negative omega into d, negative omega d. That is the phase characteristic, right? This is given by negative omega d. So this is the phase characteristic and this is the amplitude characteristics. That is for the low pass filter. And similarly for high pass filter. What is the function of high pass filter? It allows the higher frequencies and rejects the lower frequencies. It allows the higher frequencies and rejects the lower frequencies. So for high pass filter, the magnitude characteristics will look like the magnitude characteristics can be written as how? It is 1 for mod omega greater than or equal to omega c, 0 for 0 for mod omega less than omega c, 0 for mod omega less than omega c. Right? This is the high pass transfer function, high pass filter magnitude characteristics. And the phase characteristics will look like very similar to what we had. So the phase is given by theta is equals to negative omega d. So for all these filters, the phase is same. It is a linear filter. All these filters are linear phase filters. So the phase is given by theta of omega equals to negative omega d. Then we have band pass filter. Band pass filter means it allows only certain band of frequencies. It allows only certain band of frequencies. Other than that band, everything else is rejected. So how do we write the equation of the magnitude characteristics? Mod of H band pass filter of omega equals to, in which range is it 1? It is 1 when mod omega is less than omega c2 and greater than omega c1. So how can we write it? Omega c1 less than or equals to mod omega less than or equals to omega c2. It is 0. It is 0 otherwise. It is 0 otherwise. Right? It is 0 otherwise. Then similarly for band reject filter, or band reject filter is also called band stop filter. It is also called band stop filter. It's also called band stop filter. Band stop filter, if you look at this, now let us look at how low pass filter and high pass filter are related. We look at how they are related. Low pass filter and high pass filter transfer functions, how they are related. So low pass filter looks like this and high pass filter looks like this. So whatever frequencies my low pass filter is accepting or it is allowing through, those frequencies are being rejected in the high pass filter. And whatever frequencies are rejected in low pass filter, they are being accepted in high pass filter. So how can we write high pass filter as high pass filter HPF of omega, HPF of omega, it is equal to 1 minus H LPF of omega, right? If I subtract the low pass filter characteristics from a constant function of 1, right? Let the constant function look like this. It is 1. So 1 minus my low pass filter characteristics. So in the range of negative omega c to positive omega c, here I have 1 and here I have 1. So 1 minus 1 is 0, right? In the range of minus omega c to plus omega c. And similarly, outside this range of minus omega c to plus omega c, here I have 1 and here I have 0. So 1 minus 0, that is 1. So that is how we'll arrive at high pass filter magnitude response, right? So that is how I get this equation. High pass filter is nothing but 1 minus low pass filter in terms of frequency characteristics. So similarly, band stop. Band stop is also very similar. If I subtract my band stop filter or band reject filter is nothing but 1 minus H band pass filter of omega. This is the formula for band reject filter, right? That is the band reject filter. So here omega c is the cutoff frequency of omega c is the cutoff frequency for my low pass filter. Here also omega c is the cutoff frequency for high pass filter. All frequencies less than omega c will be passed through in the low pass filter. All frequencies greater than omega c will be passed through in the high pass filter. Right? Similarly, for band pass and band stop filter, we'll have two cutoff frequencies. These two cutoff frequencies will define the limits of my band, my pass band, limits of my pass band. Omega C1 and omega C2 are the limits of my pass band. All frequencies in between these two cutoff frequencies will be passed through, and outside these cutoff frequencies, everything is rejected. Similarly for band stop. So when we talk about filters, we'll talk about two different bands. One is pass band, one is pass band, and the other one is stop band. Stop band. So what is pass band? Pass band means the band of frequencies that are passed through the filter. The band of frequencies that are passed through the filter. Stop band means the band of frequencies that are stopped by the filter or rejected by the filter. Right? If the filter allows certain frequencies to pass through, those frequencies are considered to be in the pass band. Right? That band of frequencies is called pass band. The band of frequencies that are accepted by the filter are called pass band. The band of frequencies that are rejected by the filter are called stop band, right? So this is about filter characteristics. If you look at these characteristics, there is always a steep rise from 0 to 1 and steep fall from 1 to 0. In every case, there is a steep rise and steep fall. This steep rise and steep fall is not possible practically. That is why these filters are called ideal filters. Ideally, they have to be like this. Anything above this frequency must be rejected. Anything below this frequency has to be accepted. Ideally, this is the case. What happens in case of practical filters, we'll see in the coming slides. Right? So this is the ideal filter characteristics of four different types of filters: low pass, high pass, band pass, and band stop. Now we have also told that there is a all pass filter. So what is the function of all pass filter? All pass filter, it doesn't do anything. The characteristics looks like a constant function. This is mod h of HAPF of omega, right? This is my all pass filter. So what does it do? It just passes through every frequency in the signal. It does not stop any frequency. Whatever frequency is at the input of the all pass filter, it will appear at the output of the all pass filter. So this will be the frequency magnitude response of the all pass filter. Mod h of omega is always equals to 1 for all pass filter, right? Then we'll try and calculate the impulse response for an ideal low pass filter, and we should be following the same method to calculate the impulse response for any given filter. So how will we calculate the impulse response of an ideal low pass filter? So this is the formula for impulse response, right? Impulse response is nothing but inverse Fourier transform of h of omega. Inverse Fourier transform of h of omega. Now, what does my h of omega look like? H of omega looks like this, right? This is my h of omega. Actually, this is my mod h of omega. And what is the theta of omega? Theta of omega is equal to minus omega d, right? This is what we have discussed in the last slide. My magnitude characteristics and my phase characteristics. So what is h of omega? H of omega is a complex value that can be written as mod h of omega into e power j theta of omega. This is the h of omega in its polar form. So what is mod h of omega? Mod h of omega is 1. I am considering only this frequency range, and all other in the outside this frequency range it is 0. So I am only considering this frequency range. So mod h of omega is 1 into e power minus j or plus j. Theta of omega is minus omega d. Minus omega d. Right? The same thing I'm going to write there. Right? In place of h of omega, I have e power minus j omega d, and my integral limits are from minus omega c to plus omega c. In outside this frequency range, h of omega is 0. So that is why I am considering it like this. Now I will combine these e terms and write it as e power j omega into t minus d. Now let me integrate it with respect to omega. If I integrate this, I'll get e power j omega into t minus d divided by j into t minus d with limits minus omega c and plus omega c. So now I am going to substitute my limits. If I substitute my limits, this is what I will arrive at, right? 1 by 2 pi, this t minus d I am getting it inside, t minus d I am getting it inside, and here in the denominator I have j, so if I substitute omega c in place of omega, I get e power j omega c into t minus d minus, I'll substitute minus omega c, that is e power minus j omega c into t minus d. This is like e power j theta minus e power minus j theta, right? To write this in form of sine, I am multiplying it with 2 and dividing it with 2. So e power j theta minus e power minus j theta, e power j theta minus e power minus j theta divided by 2j, right? 2j. That is equal to sine theta. So in place of theta, we have omega c into t minus d. Sine theta. Theta is nothing but omega c into t minus d. So this whole thing becomes sine omega c into t minus d. And I'm cancelling this 2 and this 2. Right? So what I have pi into t minus d. Pi into t minus d as my denominator. So now I want to write this sine function in terms of sampling function, right? What is sampling function? Sampling of t is nothing but sine t by t, right? Whatever I have as my argument in sine, I should have the same thing in the denominator here. So to get the same thing in denominator, I am multiplying this whole term with omega c and dividing it with omega c. Now I'll get this omega c here. I'll get that omega c here, and this pi, I will get it outside. So what will that become? Omega c by pi, right? Omega c by pi. And then I have sine omega c into t minus d divided by sine omega c into t minus d. This is in the form of sine t by t, right? Sine t by t is nothing but sampling of t. So omega c by pi is my constant, that is my amplitude, and sampling of omega c into t minus d, that is the impulse response of my ideal low pass filter. Impulse response of my ideal low pass filter. Right? Now let me draw this impulse response of my ideal low pass filter. So this is how my ideal low pass filter will look like. I mean, its impulse response, the impulse response of my ideal low pass filter will look like. So if you look, this is my sampling function. My original sampling function is identical on both sides, right? It looks something like this. This is my original sampling function. Now what happens here, because my sampling function has been delayed, there is a negative sign here, so it is shifted towards right. By how much? By d, right? By d. So now it is centered at d. It is centered at d. It is centered at d. Then we have to see where does the zero crossing occurs for this sampling function. Now sampling of t, when is it 0? Sampling of t, when is it 0? When my t is equals to plus or minus n pi, right? When my t is equals to plus or minus n pi. So what is there in place of t here? We have omega c. Let me write it here. Omega c into t minus d equals to plus or minus n pi, right? Now t is equals to plus or minus n pi by omega c plus d, right? Plus or minus n pi or plus d, I'll take it off here and write it here. D plus or minus n pi by omega c. So for all values of t which satisfies this expression, my sampling function crosses my x-axis. It is 0, right? It crosses my x-axis. So when when n is equals to 1, what is my first crossing here? My first crossing is when n is equals to 1. D plus pi by omega c, right? This point is d plus pi by omega c. And similarly, this point is when n is equals to minus 1, that is d minus pi by omega c, right? So this is my sampling function. You can find out 2 or 3 zero crossings and leave. Then what is my amplitude at this at d? When t is equal to d, what is my amplitude in place of this? When t is equals to d, sampling of 0. Sampling of 0 is 1. And I have a multiplicative constant of omega c by pi. So 1 into omega c by pi. That is the maximum amplitude of my sampling function. That is the maximum amplitude of this impulse response of ideal low pass filter. So this is the method to find the impulse response of ideal low pass filter. What did we do? We have written the h of omega, that is the frequency response, in terms of in its polar form, the magnitude as well as phase. We have substituted that and we have integrated and found the impulse response, and we have drawn the impulse response. Since it's a sampling function, I found out the zero crossings and the maximum amplitude of my sampling function. If you look at this impulse response extends from minus infinite to plus infinite. Sampling function exists from minus infinite to plus infinite. That is, impulse response is not only defined for the positive values of t, but it is also defined for negative values of t. So I can say my impulse response is non-causal. My impulse response is non-causal, right? Impulse response is non-causal. Impulse response is non-causal. So similarly, the impulse response of an ideal high-pass filter, I can calculate. How? You can use the same method as we have done previously, or I will do like this. My high-pass filter, my high-pass filter, my high-pass filter is nothing but 1 minus low pass filter. We have seen this expression previously, right? Now I'll take inverse Fourier transform on both sides. So inverse Fourier transform of this is h of t for high pass filter, right? H of t for high pass filter, that is my impulse response of high pass filter, that is equal to inverse Fourier transform of 1 is delta of t minus inverse Fourier transform for low pass filter, that is my impulse response that I have calculated just now, that is omega c by pi into sampling of omega c into t minus d. So this is my impulse response of the high pass filter. This one also, if you draw, it will look similar to my low pass filters impulse response. The only difference being it is being inverted, right? Whatever, this is my low pass filter, this is my low pass filter impulse response, and I have a negative sign. So instead of being like this, it's going to be something like this. It's going to be something like this, right? This is how my impulse response for the high pass filter might look. And I have a delta of t also. I have a delta of t somewhere over here, right? So this one also, it is extending from minus infinite to plus infinite, right? So if you take impulse response of any ideal filter, they will have impulse response defined for t less than 0 also. The impulse response is defined for t less than 0 also. That means these systems are non-causal, these systems are non-causal, and they are not physically realizable. So what does this mean when impulse response is defined for t less than 0? That means there is some response even before I apply any input. I apply input always at t is equal to 0. But my impulse response is non-zero for t less than 0. That means I'll get some kind of response in the output even when I do not apply any input. Such filters are not realizable physically. That means practically we cannot realize such filters. So this is the criteria, Pali-Wiener criteria, that distinguishes between realizable and unrealizable filters.